Now let us see the determinant for 3 by 3 matrix, 3 by 3 order matrix. Okay, see, let us suppose this is a 3 by 3 square matrix of the order 3 by 3. Then determinant of A is, so let us represent this. See friends, represent this as plus, minus and plus. These are called cofactor signs. So it should start with plus. This is also plus, this is minus plus, this is plus minus plus. For this it is minus, it is plus, it is minus. For this it is plus, it is minus, it is plus. If you want to take any particular row or column, okay. So if I want to consider determinant through row 1, consider plus, minus and plus. Okay friends. Now it is minus 1 power 1 plus 1 into A11. Okay. Close these. See friends, close this column and close this row. What is the particular subsquare matrix that we got? A22, A23, A32, A33. Get that determinant here. A22, A23, A32 and A33. Fine. And next one. This is A12, right? So plus minus 1 power 1, 2, right? So 1 plus 2. So determinant by closing this and by closing this, we are getting these four elements, right? So apply these four elements there, A21 and A23 and A31 and this is A33. Fine. Now coming to this, plus minus 1 power 1 plus 3. Okay. Here into A12 will be there. Pardon. Okay, now into A13, right? Now by closing this column and this row, what we'll get? What we will get? A21, A22, A31, A32. Okay, A21, A22, A31 and A32. So this is the general procedure. Generally we used to follow these conventions, but in the competitive field, in the competitive examinations, we have some shortcuts how to approach in an easy way. Okay, let us see this. You already know how to calculate a 2 by 2 determinant, right? So follow this method. Or see friends, suppose this is a matrix. Listen to me carefully. First of all, I am going to tell you the shortcut now for calculating the 3 by 3 matrix determinant. See, first of all, calculate the diagonal elements product from this side. 5 3s 15, 15 1s 15. Keep it here. Okay. Calculate from this way. This way also calculate the product. 4 3s 12, 12 4s 48. Write it here. This side should be in the first. From right to left, this should be in the second box. Right? So, after that, listen carefully what I am doing. See friends. After calculating this, so we calculated the product for this material, right? So now select these two, which is parallel to this, these two elements, and opposite element is this. So 2 into 0, 0, 0 into 4, 0, plus 0. Okay friends, next. So we have selected these two, right? Now select these two, and the opposite element is this one. So minus 1 into 1, minus 1, minus 1 into 4, minus 4, plus minus 4. Right friends? Now we have completed this. Now from this row, come to this row. So 4 3s are 12, 12 4s 48. We have already written this. Now select these two, which is parallel to this. Once you selected these two, you have to select this, this element, which is opposite. So minus 2 into 5, minus 10, right? Plus. Now we have completed this. Next, take these two and select this element. So 0 into 1, how much? 0. Right? So what is the final answer? 15 minus 4, that is 11, minus 48 minus 10. 48 minus 10 is 38. What is 11 minus 38? Minus 27 is the determinant. Just to follow this method friends, it is very simple. At the beginning time you will feel that sort of confusion, but while practicing you will be it will be very much easier. Okay friends, listen again carefully. I am telling you once again. See, first you need to calculate this product. After that, select these two elements and the opposite element. first product this one, second product is 1, 2, 3. Okay, product of these 3 elements. Later, after calculating the product of these 3 elements, calculate these 2 and the product of this element, these 3 elements, right? Now the first diagonal elements are over, the product is over. Now second case, consider this one. When you consider this one, parallelly there is some elements, right? These arrow mark, this one and this element, and after completing the product, what you need to do? These 2 elements and this opposite element. Fine. So this is the one of the shortcuts that you can apply for obtaining 3 by 3 matrix of the order. Okay friends, let us see another type of shortcut. Okay. Now let us see an important tip which is useful for GATE examination. Okay, see friends, this is also a 3 by 3 matrix. So how to calculate the determinant for this matrix? See, in the first row there are no zeros. In the second row there are 2 zeros are there. In the third row there is only 1 zero, right? See, always select a row. Generally determinant means we are obtaining a sum of product for the corresponding cofactors, right? So always obtain determinant for a row which is having more number of zeros. Always select, this is not obtain, always select a determinant for a row which is having more number of zeros. See friends, listen carefully. So which row is having more number of zeros? So this, right, row 2, right? So this is plus, this is minus, and this is plus. These are cofactor signs. Now what is this? Here minus means definitely it will be plus, right? So no need of calculating minus or the determinants for 0, 0 elements. Automatically it will become 0. So calculate only for 4. It is plus 4, det of closing these and closing these. We will get 1, 3, 5, 6, right? 1, 3, 5, 6, right? Plus 4 into 6 ones are 6. 5 3s are 15. So plus 4 into minus 9, and that is equal to minus 36 is your determinant. Okay, fine. Always select a row which are having more number of zeros in order to obtain determinant for 3 by 3 matrix. Fine. So this is one of the shortcuts which is very much useful for your GATE exam to save your time. Okay friends. So now let us see the determinant for n by n determinant matrix. Okay, n by n order matrix. Let us see the determinant. See friends, it is very important shortcut, because if at all, if they might ask you the 4 by 4 order or 5 by 5 order or 6 by 6 order, this method is very helpful. Okay now friends, see. So shortcut for n by n matrix. First of all, see how many elements are there. N into n, that is nothing but n square elements are there. Right or not? So this is A11, A12, A13, so on, A1n, first row. A21, A22, A23, A2n, so on, A2n, second row. This is third row, 31, 32, 33, 3n. This is nth row, N1, N2, N3, Nn, so on, Ann, right? So take this element, 1 by A11 power n minus 2. What is n? Order of the matrix, order minus 2. Okay. Later, determinant of, see friends, carefully see. First of all, you select this matrix A11, A12, A21, A22. Find out the det and keep it here. Next, A11, A21, A13, A23. These two. Keep it here. Later, until like that, you just go on by keeping these two elements as constants. In every determinant, 2 by 2 determinant, these two elements are constants. Only in the first matrix, this will come, second one, this will come, until so on, A1n, A2n, right? Next, in the second row, see friends, carefully look at here. See, A11, A12, this element, this one and this one in the second row by eliminating this row, right? find the determinants here. By keeping these two constants, shift these two to these three. Here, right? A11, A13, A31, A33. At the same time, by keeping this one as constant until you just prolong, go on like that until the final elements A1n, A2n. This is A3n, right? Correct. Okay, friends. Finally, these two, right? Until like that, go on like this. Finally, A11 and AN1, right? Keeping these two elements constant, shift these two, this one and this one. Next, this one and this one, this one and this one, correspondingly. Keeping these two elements as constants here everywhere. Okay, friends, and finally find the determinant and multiply this one with 2, this one with 1 by a11 power n minus 2. By looking at this much of space, you feel that, oh my god, this is the toughest shortcut. No, this is a very simple model, friends. Better than application of elementary transformations to find out the determinant, this particular method is very much helpful. So now let us find the determinant for 4 by 4 matrix, then you will understand how much this method is helpful for us. Okay. Now let us find out the determinant for 4 by 4 matrix. Listen, friends, now what the shortcut I have told now, we are going to just apply that shortcut to this particular thing, right? See, first of all, what is the thing we need to consider? This element is nothing but 1 by 2 power. What is the order? It's 4 by 4, right? So 4 minus 2, determinant of, okay. Now see, friends, so what we need to consider first? So these 4 elements, right? So 2 2's 4, 4 minus 1, 3, right or not? 4 minus 1, it's 3. Next, after considering that, keeping these 2 elements as constant, we need to find out these 2. So what is the determinant for these 4 elements? 2 1's 2, 2 minus 1, it's 1, right? Now keeping these 2 elements constant, now calculating 2 1 1 1, these 2 elements, right? 2 1's 2, 2 minus 1 1, 2 minus 1 is 1, right? Now by completing these 2, we are shifting to these 2 elements, right? These 2. So 2 into 1, 2 minus 1 into 1, 1, 2 minus 1, it's 1, right? Next, these 2 elements, 2 1 1 2, right? 2 2's 4, 4 minus 1 is 3, right? Next, considering these 3, right? 2 1's 2, 1 1's are 1, so it's also 1, right? Now by finishing this row as well, now we are going to have the final row, right? So these 2 elements are common and these two will come. So 2 1's are 2, 1 into 1, 1, so it's 1, 2 minus 1 is 1. Next, 2 into, considering these 4, right or not? 2 1's are 2, 2 minus 1, it's 1. Next, now consider these 4, 2 2's 4, 4 minus 1, 3, right? Now we got the 3 by 3 determinant. So now it is very easy for us to calculate this one, right? So 1 by 2 square into, so what is the determinant for this? See, friends, I already told you a shortcut, right, for a 3 by 3 matrix. So how can we calculate? See, multiply these 3, 3 3 is 9, 9 3 is 27, right? Plus, so now first multiply these 2 with the product of this, 1 into 1 into 1, it's 1, right? Okay, it is completed. Next, product of these 2 and this 1, 1 into 1 into 1, it's 1, finish. Now go to this, now have the product of these 3, 3 into 1 into 1, it's 3, right? Plus product of these 2 in this one, how much? 3, right? Plus product of these 3, how much? 3, right? Now 1 by 4 into 27 28 29, 29 minus 3, 3 is 9, right? So 1 by 4 into 20, it's nothing but 5. So the determinant of this 4 by 4 matrix is 5 friends. So we calculated using that condensation method, that shortcut, that is also called as Chere's condensation method. So by using that shortcut and 3 by 3 shortcut, 2 shortcuts, we have calculated the 4 by 4 matrix determinant very easily. Okay, these 2 shortcuts are very important for you, so that no need of doing elementary transformations, right? No need of calculating elementary transformations, and you can find the determinant without using them, right? This is a very important thing. Okay, now let us see the properties of determinants. Okay, see friends, first property, determinant of AB equals to determinant A into determinant B. Okay, this can also be elaborated into, suppose determinant of A, B, C, D, we can write it as determinant A, determinant B into determinant C into determinant D. We can write it in this way also, right? This is one of the properties. Second one, determinant of A power m equals to determinant A whole to the power m, and m starts from 2, 3, 4. If m equals to 1, both are same, right? So no need, from 2 we can start. Okay, so determinant of A square is equal to determinant A whole square, both are same. Fine. Next, if determinant of A is equals to 0, then it is called singular matrix. Okay, if determinant of A is not equal to 0, then it is called non-singular matrix. Okay, remember these 2 names, friends. Fine. So we used to have a lot of operations regarding these 2 matrices, right? No. Okay, fine. Now, if every element of a row or column is 0, then determinant of the matrix will be 0. In the sense, if one of the row, complete row is 0, right? Completely filled with zeros, right? So the determinant of this particular matrix is 0. Not only one row, any row. Not only rows but also columns. Any one of the columns is zeros completely, then the determinant is 0. Okay, next one. Determinant of A is equal to determinant of A transpose. Both A and its A transpose determinants are same. Fine. Next one, if two or columns of a determinant are identical, if two rows or columns of a determinant are identical, then determinant is 0. In the sense, look at R2 and R3. This is R1, right? So these 2 elements are identical, same elements are there. In these cases also determinant will become 0. Not only rows but also columns. It is applicable to columns also. Not only rows but also columns. If any 2 rows or any 2 columns are identical, then the determinant will become 0. Okay, fine. Next one. If the corresponding elements of any 2 rows or columns are in the same ratio, then the value of the determinant is 0. In the sense, look at this row 3, friends. This is row 1. This is row 2 and this is row 3, right? This particular row 3 is nothing but by doing the operation R3 is equal to 2 times of R1, right? So 2 2s 4, 2 1s 2, 2 3 6 means R3 is completely dependent on R1, right? Right or not? So the determinant value also 0. So in these cases, there is a ratio between R3 and R1. That is nothing but R3 is to R1. How much? 2 is to 1. So there is a ratio between 2 rows. Then that's what he is saying. If the corresponding elements of any 2 rows, 2 into 2, 1 into 2, 3 into 2, 6, right? 2 rows or columns are in the same ratio, then the value of the determinant is 0. Fine. These are the main properties, and also there are other properties we will see now. Okay, now let us see. If any 2 rows or columns of a determinant are interchanged, then sign of the determinant changes. Listen carefully. If any 2 rows or columns of a determinant are interchanged, then sign of the determinant changes. In the sense, look at the example. Determinant 1, 2, 3, 4, 5, 6, 7, 8, 0. Am I right? So what is the determinant of this? If we calculate, we will get 27. Fine. So now what I am doing is, we are interchanging. This is row 1, this is row 2, and this is row 3, right? We are interchanging third row as first row and first row as third row. We are interchanging these 2 rows, right? Keeping R2 as constant. This is R2. We are keeping this R2 as constant. We are exchanging this, here and exchanging third row as first row, right? While we do like this, that means we have exchanged only 2 rows. Not only rows, columns also. If we do so, what we will get? The same amount of absolute values remains same, but sign changes. Here plus is there, here minus comes. When two columns or rows are interchanged in a determinant, absolute value remains same, only sign of the value changes. Okay, this is very important property. Lot of questions are being framed basing on this property. Okay, next. K into A, n by n matrix of n by n matrix with multiplied with a constant. If it is determinant, then we will have k power n into det A. See friends, if I could say, see 1, 2, 3, 4k, 5k, 7k, 7, 8, 0, right? K is only existing in row 2, right? Taking one of the k as common, keep it here. Then find the determinant and you will get the answer. If suppose, if at all, k is not like this. If k is present in everywhere, 2k, 3k, 7k, 8k and 0k is nothing but 0, right? So now how can we calculate? Take 1k from this row, 1k from this row, 1k from this row, and determinant of 1, 2, 3, 4, 5, 7 and 7, 8, 0. Right, now what we are getting? K cube into determinant of 1, 2, 3, 4, 5, 7, 7, 8, 0, right? This is nothing but, see friends, so if k is multiplied to every element, then k power order into det A. If only one element, if k is multiplied, then only 1k will come. If only for two particular rows k is multiplied, only k power 2 will come. Okay, here k is multiplied to every element, so k power order, k power its order. So this is also one of the very important properties. We will be doing questions, gate questions basing on this and these properties. Okay, these are very important properties friends. You have to understand, you have to learn and you have to memorize every day. Okay, so see the next one. 1, 2, 3, 4, 5, 6, 7, 8, 0, the determinant of this. Here what they are telling is 1 plus 4 into constant, 2 plus 5 into some constant, 3 plus 6 into some constant, means corresponding second row or third row, anything. By taking a small same constant value, multiplying with that and adding to corresponding elements, okay, with some constant and adding with the corresponding elements, multiplying this constant and adding these elements, the same determinant comes. Okay, keeping these two as constants, same determinant comes. Not only this row, even this row also we can calculate with the same value of k. Okay, now see 11th one, a plus lambda 1, b plus lambda 2, c plus lambda 3. Here there are addition of two terms, here there are individual terms. We can split this matrix into, look at this way, a, b, c, d, e, f, g, h, i, and these keeping lambdas aside and keeping the same two as constant, same should be similar to each other. Okay friends, see a, b, c, d, e, f, g, h, i, lambda 1, lambda 2, lambda 3, d, e, f, g, h, i. So these two should never change. Only when they are splitting, only these will split. They will be remaining same. Okay, did you understand? Next one. 12th one is the determinant of upper triangular, lower triangular, diagonal scalar is equal to the product of the diagonal elements. We have already seen what is an upper triangular matrix. What is an upper triangular matrix? Principal diagonal, the below elements of the principal diagonal are 0. Lower triangular matrix, the principal upper elements of the principal diagonal elements are zeros. And what is diagonal matrix? Only off diagonals are zeros, only diagonal elements are present. And what is scalar matrix? It is also a diagonal matrix, and at the same time all the principal diagonal elements are same. Okay, even identity matrix is also scalar matrix. So these particular matrices, for these particular matrices, the determinant will become the product of the diagonal elements. This is very important, the product of the diagonal elements. Okay, let us do few problems basing on that property also. Okay, now determinant will be plus or minus 1 for orthogonal matrix and for unitary matrix as well. What is plus or minus 1? It is called as unit modulus. It's also called as unit modulus. Don't get confused when this particular word is used. Okay, unit modulus is nothing but either plus 1 or minus 1. The determinant value will be either plus 1 or minus 1 for orthogonal matrix and unitary matrix. Okay. Okay, now let us see the another important properties. Okay, see determinant of A conjugate equals to determinant A whole bar. A bar determinant is equal to determinant A whole bar, or it is also equal to determinant of A theta. Fine. This is also a very important property. We know that A theta is nothing but A transpose whole bar. Okay friends. Next. Determinant of identity matrix. This value is always 1 because identity matrix is nothing but a scalar matrix, right? 1 0 1 1 1 0 0 0 0 0 0, right? So product of diagonal elements for a diagonal matrix or scalar matrix. So determinant of identity matrix is 1. Next, determinant of Hermitian matrix is always a real number. Remember this friends. Determinants of Hermitian matrix is always a real number. And determinant of idempotent matrix is 0 or 1. Either 0 or 1. That's all. No other number possible. Okay. Determinant of idempotent is 0 or 1. Next. Determinant of skew symmetric matrix of odd order is 0. In the sense, for example, what is a skew symmetric matrix? A transpose equals to minus A. Right? That is skew symmetric matrix. Skew symmetric matrix in the sense, see, suppose this is 0. This is 2i. Not 2i, 2, 3. This is minus 2, 0, minus 4, this is minus 3, this is 4 and this is 0, right? Is this a skew symmetric matrix friends? Yes, this is A transpose equals to minus A. So if we can want to calculate, this is of third order, that is nothing but odd number, order is of odd number, then you can, there is no need to find out the determinant friends, directly it is 0 because in our properties we are learning here that determinant of skew symmetric matrix of odd order is 0. Okay, and determinant of skew symmetric matrix of even order is a perfect square. What is an even order? Suppose 0, 2, minus 2 and 0. What is this friends? So what is the determinant? AD minus BC, right? So 0 minus of minus 4 is equal to 4. 4 is a perfect square, right? So determinant of a skew symmetric matrix of even order, that is 2 by 2, even order is a perfect square. Determinant of a skew symmetric matrix of odd order is always 0. Remember this. Okay. Now, next one. Yeah, look at here. Look at this question. Look at this last one. If the elements of the determinant are functions of x, and if x parallel lines becomes equal when x equals to a, then x minus a whole power k minus 1 is a factor of the determinant. This is very important. See, suppose if the elements are functions of x and if k parallel lines becomes equal when x is equal to a, suppose here x is there but we have substituted a here, then suppose here b is there, right? Suppose for example, suppose x is there. Let us think. If we substitute a in the place of x, so these two parallel lines have become equal. K parallel lines are becoming equal, right? So two parallel lines are becoming equal. So what is x? X minus a whole power 2 minus 1, that is 1. That is x minus a will be the factor. What we have substituted? A. So in that way, we will get in the place of b, if we keep a, these two will satisfy. So a minus b be the factor of 2 minus 1, that is nothing but a minus b. K minus 1, right? Two parallel lines are becoming equal. If substitute a in the place of b. If we substitute a in the place of c, what we will get? See, a square a 1, right? In the same way, a minus c whole power 2 minus nothing but a minus c. A minus b is a factor, a minus c a factor. Okay, next. If we substitute b in the place of c, so b square b1, these two will become equal, right? So b minus c whole power 2 minus 1 is nothing but b minus c is also a factor. So these are the three factors of this determinant. Okay, once go through these 20 properties. Okay friends, we will calculate many problems basing on these 20 properties which are very important in your GATE examination point of view. Fine. Okay, now let us discuss about minor of an element. Okay, see friends, if Aij equals to a matrix of order n by n, which is a square matrix, then the minor of an element, this is an element, a minor of an element Aij in A, this is one of the element in this matrix, which is the determinant of the square matrix that remains after deleting corresponding ith row and jth column of A. See, don't get confused. If you see the example, you will understand. Okay, see, if A is one of the matrix which is of 3 by 3 order, this is a square matrix. So this is the matrix and I want a minor of this element. Okay, if I want to calculate a minor of this element, see friends, just to close these two, the corresponding ith row and jth column, corresponding rows and columns are deleted, and the determinant of these four elements is nothing but minor of the matrix. Okay, next, if I want to calculate the minor of this element, okay, so what we need to delete? This particular column and this particular row. If we delete, I will get these four, right? Calculate the determinant of these four elements, you will get the minor of that particular element. So, see friends, minor calculation is very easy. Minor is nothing but a value which is nothing but the determinant of a subsquare matrix which is inside by deleting the corresponding ith row and jth column. Okay, so once you look at it and you can calculate, if suppose if I want to get the minor is always calculated by capital M, minor of 2 if I want to get the minor of capital M see, I have to delete this row and this column and this row, right? What are the remaining elements? These four are the remaining elements, right? So determinant of A11, A13, okay, and A31 here and A33, right? So what is the determinant? Tell me. A11, A33 minus A13, A31. This is the determinant, right? Okay, friends, now we are going to see minors are always calculated in terms of their corresponding submatrix order. Listen carefully. See, what is in a subsquare matrix? Now I am going to explain. Listen. The number of subsquare matrices of order R in any matrix of order m by n is equal to MCR into NCR. These are called combinations. I will be discussing these combinations in permutations and combinations before probability. Okay. See, let us apply this formula in this particular questions and then you will understand. See friends, suppose I have a matrix 1, 1, 2, 2, 1, 2. This is a rectangular matrix of order 2 by 3. In this matrix, how many total number of minors are there? So this is the question he might ask you in your GATE exam. See, how many elements are there? Total 6 elements are there. Yes or no? In this 6 elements, see, what is a subsquare matrix? See, this is a square matrix, one subsquare matrix. This is one subsquare matrix and this is another subsquare matrix, 1, 2, 2, 2. Right? So these are the subsquare matrices. How many 2 by 2 subsquare matrices are there? 3 are there. There are 3 2 by 2 subsquare matrices are there. Right? So how can we get that C? By using this formula, we can calculate subsquare matrices of order 2 by 2. See here in this 2 by 3, this is M, this is N, right? So 2C2, because we are calculating 2 by 2 subsquare matrices, right? 2C2 into 3C2. What is this 2? Nothing but what particular order we are calculating the subsquare matrix is the R, and M and N are 2 into 3. So by calculating 2C2 into 3C2, 2C2 is nothing but 1, 3C2 is nothing but 3, that is nothing but 3. Now 1 by 1 matrix. See friends, listen carefully. In 1 by 1 matrix, how can we get 6? See, 2C1 into 3C1. Mn, R value is 1, right? So 2 into 3 is nothing but 6. Now what are the total number of minors? 3 plus 6, it's 9. In the sense, in the matrix of 2 by 3, okay, rectangular matrix 2 by 3, how many total number of minors are there? Total 9 number of minors are there. Okay friends, remember this formula, it is very important. Okay, now let us see here. Here in this question, there are total 12 number of elements are there. Yes or no? 3 by 4 is the order. See friends. Now, how many subsquare matrices are there? See friends. 3 by 3 subsquare matrix. This is one 3 by 3 subsquare matrix. This is another 3 by 3 subsquare matrix. Am I right? This is another 3 by 3 subsquare matrix. Am I right? And this is another 3 subsquare matrix. Right? So how many we are getting? Total 4 we are getting. So in order to overcome the confusion, simply apply this formula. So what is the value of M? This is M and this is N. So 3 by 3 matrix, right? So 3C3 into 3C4, 4C3. MCR into NCR, right? 3C3 into 4C3, right? 3C3 value is 1, 4C3 value is 4, total 4. Next, 2 into 2. So how many 2 by 2 matrices we are going to get? So no need of doing like this. It's a sort of confusion. Just do apply the formula. By applying the formula, we are going to get as, let me erase this. Now see. Yeah, see, now in 2 by 2 matrices, how many minors are we are going to get? See, 3C2 into 4C2. That's nothing but by applying the formula we got this. 3 into 6 equal to total 18 number of 2 by 2 minors are we are going to get. Now how many 1 by 1? Simple friends, 1 by 1 is nothing but total number of elements only. Okay, here total number of elements is 6 and here total number of elements is 12. Simple. Fine. So how many total number of minors are there in this 3 by 4 particular rectangular matrix? There are total, this is 30 and this is 34. Total 34 minors are there. Okay, so in this way you need to approach if they ask you about the total number of minors in any particular matrix. Okay. Okay, now let us see what exactly a cofactor of an element. Fine. See friends, if A is a matrix of order m by n, then the cofactor of an element Aij is denoted by capital Aij and is defined as minus 1 power I plus j into minor of that particular I row jth column. See friends, listen carefully. Cofactor is nothing but for every element we will calculate the cofactor. Right? For every element we will calculate cofactor. See, suppose it is a 3 by 3 matrix. Right? For this element one cofactor will be there. This element cofactor will be there. For every element cofactor will be there. How to calculate cofactor for this element? See. So this is the formula for the cofactor and the cofactor is denoted by capital Aij. So capital A11, right? This is 11, right? A11, right? So capital A11. So how to calculate for this is nothing but minus 1 power 1 plus 1. What is the minor? What is the minor of this one? Minor means deleting one column and deleting that corresponding row. So 5 into 0, 0. So 5 into 0, 0 minus 6 into minus 1, it's minus 6. So minus 1 power 2 into 6. This is nothing but minus 1 square, it's positive 6. So what is the corresponding cofactor of this element is nothing but plus 6. Now let us calculate cofactor 32, A32. See friends, so what is the formula to find the cofactor? A32 is equal to minus 1 power 3 plus 2 into, what is the minor of 3, 2? This is the third column, third row, second column, right? For this we are going to calculate the minor of the matrix. Now, deleting these two, we are going to get 1 into 6. 6 minus 4, 3 is 12. 6 minus 12. That is nothing but minus 6. Minus 1 power 5 into minus 6. This is nothing but minus 1 power odd number is negative, right? So minus into minus 6, that is nothing but plus 6. So cofactor of A32 is nothing but 6 friends. So in this way, if we calculate all the cofactors, suppose for example, we will calculate cofactors in this way, and if we arrange the particular cofactors corresponding to these elements in such a way that, suppose for example, if A is a matrix, there is a matrix A11, A12, A13, A21, A22, A23 and A31, A32 and A33. If there is a matrix, so we are calculating the cofactors for every corresponding element. If for the A11 I got a cofactor matrix. Now I am writing the cofactor matrix of this matrix. See, what is the cofactor of A11? Capital A11. What is the cofactor of A12? Capital A12. Like that, if I calculate everything and arrange in this way, corresponding to elements in the respective positions, A21, A22, A23 and A31, A32 and A33. Okay, this is the cofactor matrix. Okay friends, and another important property of cofactor matrix is determinant of cofactor matrix is equal to det A power n minus 1. In the sense, from this matrix, from the A matrix, we determine cofactor matrix. What is the determinant of this cofactor matrix? See, nothing but det of A whole power n minus 1. This is the order 3 by 3, right? If determinant of this matrix is 5, if suppose, so 5 power 3 minus 1, that is nothing but 5 square, 25. So if the determinant of the matrix is 5, then the cofactor matrix determinant is 25. Fine? Did you understand? If suppose, if the determinant of this matrix is 3, what will get? If suppose it is a 4 by 4 matrix, suppose A41, A42, A43, okay, and A14, A24 and A234 and A44. If suppose it is a 4 by 4 matrix, fine, and the determinant of this matrix is 3. Let us suppose that is equal to 3. So A14 here, this is A24 here, see A34 here, and again we will be getting, see friends, A41, A42, this is A43 and this is A44. So what is the determinant of this matrix? This determinant is 3, we just assumed. Now what is the determinant of this cofactor matrix of 4 by 4 order? Tell me, the formula is det A power n minus 1, right? What is the det? 3. 3 power, what is the order of this matrix? 4. 4 minus 1, that is nothing but 3 cube. 3 3 is 9, 3 is 27 is the determinant. In this way we will calculate. Remember friends, cofactor matrix determinant is nothing but det A power n minus 1. Okay? Okay. Now friends, we are going to talk about adjoint of the matrix. Fine. So what is adjoint? Suppose if B is a matrix of order n by n, which is a square matrix, is a cofactor matrix of A. Suppose A is a matrix that we are having, and we found a cofactor matrix that is B. Then the adjoint matrix of A is denoted by adjoint A, ADJ of A, that is adjoint A, and is denoted by B transpose. In the sense, adjoint A is nothing but the transpose of cofactor matrix of particular matrix. Adjoint of particular matrix is equal to this cofactor matrix transpose. Fine. The cofactor matrix, we already saw how to define a cofactor matrix. If we put a transpose symbol and find out that is nothing but the adjoint. Right? See friends, for example, this is the matrix. So for this matrix we will define cofactor matrix, that is A11, capital A11, capital A12, capital A13. In the same way, if we apply transpose to this cofactor matrix, we will get the adjoint of this matrix. Fine, this is the adjoint. So this is row 1, this is row 2, and this is row 3 friends. So these rows are interchanged into columns. So this is the cofactor matrix transpose, that is nothing but adjoint of the matrix. So no need to find out all the minors, no need to find out all the cofactors and writing those cofactors in certain order, no need. I will be telling you a shortcut, follow that shortcut. For any sort of question regarding adjoint, you will get definitely within short span of time, you are going to find out the answer. Okay? Okay friends, now let us see the shortcut to find the adjoint of the matrix. Okay, see carefully. So this is the matrix he has given. So this is the matrix 1, 2, minus 1, 0, 4, 3, 5, minus 2, 1. Right? Listen to me carefully. First write this column, extend here 1, 0, 5. Extend the column. Extend the second column as well. 2, 4, minus 2. I am telling you the shortcut. This is not the original procedure, which is very useful in your GATE exam. Okay. After extending these two columns separately here, now extend first two rows obtained again once again here, right? So again first two rows as it is 1, 2, minus 1, 1, 2. Second row 0, 4. 3, 0, 4. Okay, so what we need, we got. See, now what we have to do is eliminate first column and eliminate first row. Okay, this is the next step. Now what you have to do is, listen, we already know that adjoint of a particular matrix is equal to the cofactor matrix whole transpose, right? So Now see friends, this is one particular matrix, this is a one particular matrix, and this is a one particular matrix. Whatever be the determinant that you are going to find here, that is a minor you are going to find here in a vertical line, you apply these three minors in a horizontal way. Or else, if we want to apply for these three, one, now see, first one, and this is the second one, this is the second one, and this is the third one. If you want to calculate these three, 1, 2, 3, apply vertically the values. Okay, if you are going through vertically, apply the values horizontally. If you are going through horizontally, apply the values vertically. In that way we will get the adjoint of the matrix. See friends, see carefully. After doing all these things, extending the columns first, extending the rows next, and deleting the first column and the first row, now we are going to get the minus. See, 4 into 1, 4, right? Minus 2 into 3, minus 6. That means here plus 6. 4 plus 6, 10. We got one element. Next, minus 2 into minus 1, it's 2, right? Minus 2 into 2, 2 into 1, 2. 2 minus 2 is 0, right? So we are going horizontally. That means I should keep 0 here, right? Now, 2 3s, 6. 6 minus 4 into minus 1, minus 4, that is here plus 4. 6 plus 4, it's 10. Once again, 10 here, right? So, since we have went vertically, the answers should be, minus should be horizontal positions. Now, going through these two, 15 minus 0, 15. Next, 1 minus 1 into 5, minus 5, that's plus 5 here, 6 here. Minus 1 into 0, 0, minus 3 into 1, 3, minus 3. Next, these two, 0 minus 5 4 is 20, it's minus 20. Next, 5 2 is 10, 10 minus 1 into minus 2, it's plus 2, it's 12. So this is 12 here, and 4 minus 0, 4 here. So this is the adjoint of the given matrix. Within one step, within one calculation, no need of finding cofactor matrix and doing transpose to that again, no need, it's a waste of time. So in your competitive exams, time is very important parameter. So use these shortcuts, then you will find within less span of time you will find this. But be careful, don't apply the minus as you move forward, as you move horizontally, don't apply the minus in horizontal position. If it is you are going vertically, then put in a horizontal way. You are going horizontally, then put the minus in vertical way. Fine. So this is the very good shortcut for adjoint matrix. Okay. Okay, friends, now let us see the properties of adjoint of the matrix. Hope you understand the shortcut of the adjoint. Now let us see the properties. Okay, see friends, first one, A into adjoint A equals to adjoint A into A equals to determinant A into I. In the sense, if suppose if the determinant value of A is 5, so if we multiply a matrix with its adjoint matrix, or if we multiply an adjoint matrix with the normal matrix, then if the determinant of the matrix is 5, 5 0 0 0 5 0 0 0 5, this is the matrix that we are going to get. This is what exactly mean 5 into I, right? So this is the way you need to understand. So A into adjoint A equals to adjoint A into A equals to det A into I. Now adjoint of null matrix of order n is nothing but null matrix itself. Next, adjoint of identity matrix is identity matrix itself. If D is a diagonal matrix, adjoint of the diagonal matrix is also diagonal. And if suppose if A equal to LMN, diagonal LMN, what is the answer that we are going to get when we apply adjoint? Listen carefully, this is a shortcut. Here L is there, so in the place of L, the product of other two elements will come 0 0 0, and here M is there, so the product of other two elements will come Ln, and if here n is there, the product of other two elements will come in the adjoint. This is LM. Fine friends, did you understand? So it is very easy to calculate the adjoint for a diagonal matrix. Fine, use this shortcut. Next, adjoint of A transpose is equal to adjoint A whole transpose. You can find after calculating transpose, then you can find adjoint, or first you find the normal adjoint and then find and apply the transpose. Both are same. Next, adjoint of A theta equal to adjoint A whole theta. Same. Next, sixth one, adjoint of AB equal to adjoint B into adjoint A. First B will come here, then A will come here. Remember. Okay, next, if determinant is equal to 0, then adjoint A determinant is also 0. What is determinant equal to 0, friends? That means the matrix is singular matrix. When the matrix is singular, the adjoint of that matrix determinant is also 0. Okay, next, what is the determinant of adjoint A? This is a very important formula. This is nothing but det A power n minus 1. See friends, cofactor determinant, adjoint determinant, both formulas are same. Det A power n minus 1, where n is the order. Okay, next, A into adjoint A, adjoint of adjoint A. See friends, adjoint of adjoint A is nothing but det A power n minus 2 into A. This is also a matrix. You can, if he has given a normal matrix and he has asked adjoint of, find the adjoint of adjoint A, then apply this formula. Determinant of this matrix power given order minus 2 into normal matrix product. Okay, next, what is the determinant of this matrix? He has asked here. Then adjoint, det A whole power n minus 1 whole square. Here only one adjoint is there. That's why here whole power 1 came. Here two adjoints are there. That's why whole square came. Here three adjoints are there. That's why whole cube came. That is the logic. Okay, did you understand? Now, adjoint of K power n minus 1 into adjoint A, where n is the order of matrix A. Okay, adjoint of K is where K is a constant, which is a scalar, K power n minus 1 into adjoint A. Okay, next, if A is a 2 by 2 matrix A, B, C, D, then adjoint A is nothing but D minus B minus C A. D minus B minus C A. Okay friends, next, if A is a Hermitian matrix, adjoint A is also Hermitian. If A is a symmetric matrix, then adjoint A is also symmetric. Remember these 15 formulas, which are very important, and majorly you need to focus on these things from 6 to 13. And another important formula is this, fourth one. Okay friends, main important things. So because in further we have to do a lot of problems and get questions also regarding these formulas. Okay, so I hope you understand about the adjoint. Okay.